Okay. This time I'm going to be talking about language modeling and neural networks, kind of two things at once. Both introducing the task of language modeling and introducing the modeling tool of neural networks. So what is language modeling? Language modeling is basically a task of determining whether a particular sentence or text is likely to occur. And so to do an example of this, we can take a look at these sentences and see if they're okay. So what about this sentence? Does this look reasonable in English? See people nodding, yes. What about this one? No, okay, yeah. That's the easy one. This one? No, yeah, not that great. Maybe a 3 or 4 year old might say it, but probably not an adult.
Or Tarzan.
Or Tarzan, yeah. There's that. What about that one? Yeah, it's pretty similar. You know, maybe a 3 or 4 year old might say it, but what about that one? What do people think? In some contexts, it might be happening. What about that one? Sure, yeah. And a food truck is kind of a type of a store, right? You know, if you think about it. So if we wanted to create a model to handle these, like let's say we wanted to create a rule-based system that told us whether these were correct or not, like we did before. We could do this by creating a grammar of the language, and we're actually going to be talking about, you know, parsing and context-free grammars and ways you could kind of even manually create a grammar that would allow you to decide whether the grammar is correct. Consider morphology. We're also going to talk about morphology, which is basically conjugation of words, and decide what the exceptions to those are. So, you know, goad might be okay if it was a regular verb, but go is not a regular verb. So we need to say when. Also, semantic categories. Stores are not something that tend to go somewhere, right? And there are exceptions. So a food truck might be a type of store according to some sort of ontology, but at the same time, it's a mobile one, so it can go places. So one other interesting thing that I didn't write on the slide is that actually with more and more powerful language models also can make distinctions between other things like factual correctness. So, you know, could say something like Carnegie Mellon University is in, which would be correct syntactically, semantically, well, syntactically and according to selectional preference to say New York, but it would be wrong, right? So there's a whole lot of things that go into a language model judging whether a sentence is appropriate. And these are just some examples here. So because it would be difficult to create, you know, a model in a rule-based system, just like it is for text classification, we come up with probabilistic language models, and we talked about these in the last class. Basically, they're models that try to calculate the probability of a text, p of x. And the standard way we do this, it's not the only way we do this, but the standard way we do this is by decomposing and calculating the next word in the sentence given the previous words of the sentence. From a probabilistic point of view, we could do the previous word in the sentence given the next words in the sentence. We could model language from right to left, or more accurately from, when we say left to right, this is kind of an English bias because some languages are written from right to left, like, you know, Hebrew or Arabic or something like this. However, another way to think of it is from past to present. So basically, the order in which words are spoken in the language, and that's kind of a natural ordering, right? It's the same order in which humans consume information. So it kind of makes sense that we might want to model language this way. So yeah, that's the next word, that's the context. So the big problem becomes, how do we predict this? And I'm going to talk about two different ways. Count-based models and learning-based and feature-based models, including both log linear models and neural network models. Before getting into that, though, I'd like to talk a little bit about what we can do with language models. And basically, there's a couple things. The first thing, if we ignore the type of language model and say just we have any language model that can calculate this probability, there's kind of two major things we can do with them. The first thing is score sentences. So we have multiple sentences or multiple words, and we'd like to score their probabilities and say one is more likely than the other. So this is one example. We could say Jane went to the store and give it a high probability, or store to Jane went the, give it a low probability. This is kind of a contrived example, but what are some other real applications that we might be interested in where we could use a language model like this? Any ideas? Things that you might use pretty frequently. Yeah. For speech recognition? Yeah, so the answer was you have speech recognition and you'd like to use the language model to determine which of the two words would come next if they sound similar. Yeah, that's a very good example. I got that in the, not Slack, sorry, Zoom chat as well. In the Zoom chat, I also got evaluating the quality of machine translation. This is, yes, something you can do. You can take a look at whether the machine translation looks fluent. I also got spelling and grammar checking, yes. In fact, I don't know if people have noticed this, but the Google Docs grammar checking is frighteningly good right now. Like in the past year or something like that, it's gotten a lot better. I don't know what's going on inside, but I imagine they have a language model as part of it as well. Another example that nobody answered, nobody said here, but is nonetheless maybe an interesting one, is question answering. So you feed in a question to a language model, and you ask it to choose between one of several multiple choice answers, and it would be able to choose, it might be able to choose the correct one. So that would be another example. And another thing you can do is generate sentences. So if you have a language model and maybe you give it some sort of prompting and say, this is a story about a blue dragon that lived in the forests north of Pittsburgh or something like that. If you have a really good language model, it might tell you an interesting and compelling story about a blue dragon in the forest north of Pittsburgh. If you have a poor language model, it would give you, word soup or something. So this is another thing that you can do with language models. So basically scoring multiple options or generating new sentences from scratch. So first, like I did before, I'm going to start with count-based methods. And part of the reason why I'm going to start with count-based methods is, number one, historically, count-based language models were used for a very long time. And the second reason why I'm going to talk about them is because I think thinking of the difficulties in using count-based models is a very good motivation for why we might want to use something like neural networks, which I'm going to introduce later in the class. So we talked about count-based unigram models last time. So I'm just going to go through it very briefly. Count-based unigram models, basically what they do is when they're calculating the probability of the next word, they assume it's independent of the context. And then we count up the number of times a particular word appeared in the corpus and divide by the total number of words in the corpus. And then we interpolated this with an unknown word model to make sure we could generate any word that we wanted. So I think everybody remembers this, just a refresher. So let's say we wanted to create a model that actually did have some idea of how words could be used in context. One way we can do this is using something called a higher order n-gram model. And so the unigram model is basically a model that only considers a single word, the current word. You can also have something called a bigram model that considers 2 words, a trigram model that considers 3 words, et cetera, up to as many as you want. You could use 10 grams, 15 grams, whatever. So what you do is you basically limit the context length to n. You use the n-1 previous words. You condition on the n-1 previous words, and you count the number of times this word has followed another word. So just to give an example, let's say we wanted to calculate the probability of seeing the word example, given that the previous 3 words were this is a. And so this is n. And given the previous words like this, we would calculate the number of times we saw this as an example, and we would divide by the number of times we saw this as n. However, this is a problem because if we set n to be very large, or we have a context that we haven't seen very frequently before, it's very likely that the actual continuing word is not going to be seen. So basically what we do is we take the maximum likelihood estimate of the current word. For example, this is an example. And we interpolate it with a probability from a lower order. So basically we would chop off the first word in this context here and just condition on is an example. Sorry, that's a typo, is an example. And then we would continue doing this all the way until we got down to a unigram model. So we would condition on the longer context if we could. If we had sparsity and weren't able to use the longer context, we would condition on the shorter context. So there's lots of different smoothing methods that we could use. We actually talked about +1 smoothing last class, if people remember this. I'm just going to cover this very briefly here. If this was a NLP class, several years ago, I would have covered this in a lot of depth because it was really important. But now we generally use neural networks to handle this for us. But basically, what additive smoothing does is it adds a little bit of probability that can be used for the lower order models. So we have this fallback distribution here, which might be the fallback, the distribution where we condition on less context than we did before. And then we have this interpolation hyperparameter where basically we add a certain amount of probability to each context. So if we have, for example, if we have a context that's only appeared 1 time, like let's say we only had 1 example of a context, and let's say our alpha was 1, we would allocate 1/2. We would allocate 1/2 of the probability for the actual word that we saw in that context, and 1/2 of the probability to the fallback distribution, to the distribution that conditioned on less context. Another method that you can use is something called discounting. And what discounting does is it has this discount hyperparameter. And so like, let's say our counts were, let's say we had a count of a context equal to 1. We might subtract a certain amount of from that value. So instead of having, let me give an example. If we had the 2 examples, this is an example and this is an apple. And this is an example had a count of 2. This is an apple had a count of 1. We would subtract the discount. Let's say it's 0.5 from each of these. So then this would become 1.5. This would become 0.5, and then we would take all of the stuff we subtracted and add it to the lower order distribution. So the lower order distribution would get a count of 1, basically, would get a pseudo count of 1. And so here, the only hyperparameter is this discount, and the interpolation coefficient here can be calculated by the sum of the discounts. So you saw that the amount of count that we assign to the lower order distribution is 2 times the discount, because there are 2 unique contexts here. So there's a whole bunch of other variations of this. The one that is basically state of the art for count-based n-gram language modeling, or has been for a very long time, is Kneser-Ney smoothing. It's basically discounting with some modifications of the lower order distribution to make the statistics work out, so that when you're falling back to the lower order distribution, it's more appropriate. I'm not going to go into all of the details, but there's a really good paper, an empirical study of smoothing techniques for language modeling by Goodman, that you can read if you would like more details on this. Yes?
Are you subtracting the fallback distribution?
Oh, sorry, that's a typo. That should be added. Yeah, thank you. In case you missed it, it said the question was, should you be subtracting the fallback distribution in the discounting slide? And no, we should be adding it here. So you're adding the probability from the fallback distribution. I have 2 questions from Zoom. One is, why is there an alpha in the denominator? There's an alpha in the denominator because we're adding it to the numerator, so we need to be adding it to the denominator as well to make sure everything is 1. We don't need to add it. We don't need to add it here, and the reason why we don't need to add it in discounting is essentially because we are subtracting the count from here, and then we're adding it back in here, so it's okay. Everything adds up to 1. If you go through the math a little bit, you'll be able to see that. The other question, do I have a darker whiteboard marker? Yes, I do, and I will use it next. Thanks for pointing that out. Okay, great. So this is just kind of a high-level overview. This can be useful to know if you're doing count-based estimation for whatever reason, and there are reasons why you would like to do it. I'd like to point out here some of the problems that standard n-gram models face. And one of them is they cannot share strength among similar words. They cannot share statistical strength. So let's say you have some training data that used bought and purchased, or that has bought and purchased in the context. If you've seen she bought a car, she bought a bicycle, she purchased a car, but you have not seen she purchased a bicycle, basically you would have issues with predicting the probability of bicycle here, because there's no way to share information about the fact that she bought a bicycle is plausible, or like bought and purchased are similar and car and bicycle are similar. So this is a really big issue. Another issue is that you cannot condition on context with intervening words. So if you had an intervening unusual word here, basically your context would be destroyed, and it would have to fall all the way back to a unigram model, because it hasn't seen Gertrude very frequently in the corpus. So despite the fact that Dr. something Smith is a very likely thing to see, you would not be able to estimate this probability well. And another issue is that it cannot handle long distance dependencies. So like something like for tennis class, you wanted to buy his own racket. For programming class, you wanted to buy his own computer. It's not, because we are limiting the context to, n-1 words, it would have trouble modeling these probabilities. So interestingly, within count-based models, everybody knew these were problems, and they devised solutions. So they devised solutions like class-based language models, skip-gram language models, which basically skip a word, cache, trigger, topic, or syntactic models that allow you to handle long-distance dependencies. And there's actually a really nice paper called A Bit of Progress on Language Modeling. This is a pun. And the reason why it's a pun is because a bit is like information theoretic measure. I'm going to talk about entropy later, but it's basically a pun. But they went through and tried all of these, combined them all together, wrote an 80-page paper about it, and it was a huge engineering effort. So I think one interesting thing is, I'm going to be talking about neural networks later in this class. And one of the attractive things about neural networks is it's not that there aren't ways to solve all of the problems that I talked about here. It's that it's very easy to solve all of these problems all at the same time with neural networks, at least to some extent. But it's very hard to do it if you have to come up with custom solutions based on count-based models. So I think that's the big thing to think about as we go forward. Yes. Class-based language models. So basically what class-based language models did was they grouped words into classes. So you would find like bought and purchased could be combined into a single class. Bicycle and car could be combined into a single class. And basically what you would do is, instead of calculating the conditional probability of the next word given the previous words, you would calculate the conditional probability of the next class given the previous classes, and then you would calculate the probability of the word given the class. And that would help like alleviate sparsity. So it's actually pretty similar to embedding-based models that we're going to be talking about soon. I'll draw some more parallels to those later after we finish. Yeah. Okay, yes, another question. No, the classes would be induced automatically. So the way that people induced classes was basically by, for example, an iterative merging algorithm where you would merge two words into the same class in a way that maximized the predicted performance of the language model. So you basically merge words where if you merged those two words together, the language model would still have good performance. It's a method called Brown clustering. The interesting thing is this method of Brown clustering actually shares a lot of similarities with like word2vec, if you know of word2vec. And there's also some interesting observations that mirror the word2vec paper in this paper that came out in like 1995 or something like this. So, yeah. Anyway, that's a kind of a aside. Okay. So I think most of the time you will not be using these sort of count-based n-gram models. They're mostly useful for their intuition. However, there are a few times when I do recommend that you use them, despite the fact that neural models generally achieve better performance. N-gram models are extremely fast to estimate and apply because all you have to do is count and divide. The counting can be done completely parallelized. So you could parallelize it over, millions of machines using MapReduce or something like this. Another thing is n-gram models can be better at modeling low frequency phenomena some of the time. N-gram models are non-parametric models, which means that they basically can add more parameters as your data size gets larger. And these models in general tend to be good at modeling things that don't occur very frequently. So they actually have advantages in some cases where neural models do not. So if you want a really easy way to do scoring of sentences or something like this, you can use KNLM. It's a very fast estimated. It'll be 100 times faster than any neural language model you're learning. So you can try it out.
Don't say this too often. Ken is also a graduate of our program.
So Bob will be the person who reminds me when I introduce people who graduated from LTI. So Ken also graduated from LTI. Did this while he was here at LTI, actually. So, it's a very popular tool. Okay. So now we have a way to estimate language models. How do we figure out how well they're doing? So the standard ways to do so are basically like what we did for text classification. We have a training set, a development set, and a test set. And actually, sorry, I should have changed the variables here. This should be, I should just write that as X, not E. So assume that this is just a sentence. So one way we can evaluate language models is through the log likelihood. And the log likelihood is just a log probability of all of the sentences in the test corpus or all the documents in the test corpus. One issue with log likelihood is that if you have two corpora and you want to compare your log likelihood across them, they won't be comparable. So what we do is we divide by the number of words in the corpus overall and get the per word log likelihood, and this makes it approximately comparable across similar size corpora. We also talk about entropy, and entropy is the negative log likelihood, usually the negative log 2 likelihood of the corpus with respect to per word. The reason why we use entropy is entropy actually has a very nice connection with information theory, and it's basically the lower bound on how well the model could compress this text. So basically, if you have a language model that you train to model Wikipedia or something like this, and then you feed in if you feed in all of Wikipedia into this language model and use a very good compression algorithm, the number of bits required to compress the Wikipedia corpus would be equal to, or would be lower bounded by this cross entropy. So the interesting thing is that, language models can also be used as text compressors. So if you have a better language model, you could also get better text compression and make a smaller Wikipedia dump or something like this as well. Then the final thing is perplexity. So this is probably the most common thing that you see in papers on language modeling. Perplexity is the exponentiated, is taking the per word cross entropy or per word log likelihood and exponentiating it appropriately. And perplexity, tends to be in the range of, like, for language modeling, something like 10 to 50 or something like this. And the interpretation of perplexity is, if you took the language model and based on its probability, according to its probability, you randomly guessed the next word, perplexity is approximately how many times you would have to guess before you got the correct word. So if your language model has perplexity of 10, and you guessed the next word according to the language model's probability distribution, you would get the answer right in about 10 times on average. Yeah. Yes.
So there's no ground truth here, of course, it's just text from a corpus representing the language model, correct? So if it's a well-formed sentence, a good language model will show high probability. Is that the point?
So that's a really good question. So note that we're evaluating this on the test, on a test corpus, held out test corpus or development corpus that is not included in our training data. So in a way, this is the ground truth. This is some text from the distribution we're interested in that actually occurred somewhere in the, on the internet or, elsewhere. So how high a probability our model gives to that is, a pretty good measure of how good the language model is. And the reason why is because in order to give that text high probability, it has to give low probability to other text that is not natural, because all probability has to add up to 1. So if you're going to give more probability to one thing, you've got to take it away from something else. Right. So this is also a good point. What language modeling is doing is it's not modeling syntactic text versus non-syntactic text. It's also not modeling semantically correct text versus non-semantically correct text. It's modeling likely text. So it's modeling text that it thinks it's likely to see in the future. So there's all kinds of things that factor into that, whether it's syntactic, whether it's semantically correct with respect to something that actually could happen in the world, and also maybe whether it's correct with respect to something that it actually did factually happen in the world. So all of these things are conflated, basically. Yeah.
Would you say this is similar to Huffman coding, where something which is more frequent gets like a smaller?
Really good question. So is this similar to Huffman coding, where something frequent gets, where frequent things get longer codes and infrequent things get shorter codes? Sorry, other way around, yeah. Frequent things get shorter codes and infrequent things get longer codes. Yes, it's precisely like that. And basically there's a way, I'm not going to explain the details here, but if you're interested, you can look it up. There's something called arithmetic coding. And basically what arithmetic coding allows you to do is it allows you to turn any probability estimate into a code where any probability estimate over discrete things into a code, even if that thing is like variable length or something like this. So here, it's kind of like Huffman coding, but for a very large set of things over, variable lengths. So if you have a good language model, you can basically put that into the arithmetic coding algorithm, and higher scoring sentences will get shorter codes. Lower scoring sentences will get longer codes. Yeah. Very good questions. Okay. One comment is about unknown words. So we talked about unknown words last time as well. We need to be able to handle them because we won't have all the words in the world in our training data. And larger vocabularies require more memory and computation time. There's some common ways to do this. So we can limit the vocabulary by a frequency threshold or a rank threshold. So basically, if the vocabulary only occurred in our training corpus, a certain number of times, then we make it an unknown word. Another more common way to do things nowadays is to model characters and subwords. So we train a language model over characters, or we train a language model over kind of sequences shorter than words. I'm not going to talk about this in a lot of detail now, but we'll definitely cover it later. When you're doing evaluation, one thing you need to be careful of is the vocabulary must be the same over the models you compare, or more accurately, all models must be able to generate the test set. So what I mean by this is it's not fair to compare a character-based model to a word-based model if the word-based model is using unknown words and the character-based model is not. So just to give an example, like an intuitive example why this is not fair. What's a unusual city name?
Wilmerding.
Wilmerding, okay. I don't know if I got that right, but perfect. So if we ask our character-based model to generate I am from Wilmerding, and if we ask our word-based model to generate I am from Unk, it's a lot easier to generate I am from Unk than it is to generate I am from Wilmerding. So basically, If you're comparing like a word-based model and a character-based model or something like this, you should make sure that the word-based model is being required to generate the unknown words in some way, like with a sub-character-based model or something. Or the character-based model is actually generating I am from Unk, which is kind of a strange thing to do, but yeah.
It's interesting, you were able to generate Wilmerding without knowing it because of your character-based.
Yeah, and I was able to generate Wilmerding without knowing it because I have a character-based model in my head. That's probably, I'm a fan of character-based models. I'm less of a fan of subword-based models, but I'll live with them. But basically, this is something important to know if you're comparing different types of models. Okay. So next, I'm gonna maybe pick up the pace a little bit so I don't run out of time, but we have an alternative to count-based models. And these are featurized log linear models. If Bob wants to point out that Roni Rosenfeld is a faculty member at CMU NLP, he can. But this is, so basically the idea here is we turn the language modeling problem into basically a classification problem. And specifically, what we do is we calculate features of the context, and based on the features, calculate probabilities, and optimize the feature weights using gradient descent. So what we did before, remember we did text classification, we calculated features of a input sentence or text, and calculated the probability of an output label. Here, our output label is simply the label of the next word. And just to give an example, if we have the context giving a, like giving a talk or giving a lecture or giving a present, we would calculate all of the features of the context. So we could look up features like this and have a bias and add them together and calculate scores. And from the scores, calculate probabilities. And here, this is the simplest variety of such a model, where basically each word is associated with scores corresponding to how much more likely the word occurs, or the next word is to occur given that the previous word has occurred in the context. And if we think about it, this is a lot like the bag of words classifier that we talked about before. The main difference from the bag of words classifier is that the bag of words classifier had a single lookup, had a single feature for each word in the sentence. Here we have different features for each position of the word in the sentence. So essentially we have a feature corresponding to the fact that we saw giving 2 words ago and 1 word ago. So just to make this a little bit more concrete, if we look at the words that we're predicting, this would be like over our entire vocabulary. We would calculate a bias. So this is how likely are words in general. So of course, and da are very likely words, so they would have a very high score. Things like talk or gift would have a little bit of a lower score. Then we have a weight corresponding to whether the previous word is So given that the previous word is it's very unlikely that the next word is going to be or the, especially comparatively compared to the overall probability. And then we'd also have a feature corresponding to how likely something is given that the second previous word is giving. And this might upweight talk or gift because these are things you tend to give, right? Then we combine all of these together into a score and feed the score into the softmax function to calculate a probability. So you can see that this looks a whole lot like our text classifier, right? You know, we're looking up features, we're adding them together, we're calculating probability. For the training algorithm, we can calculate the gradients of the loss function with respect to the parameters. We're going to use the chain rule or back propagation for this, more in a second. And we update to move in the direction that decreases the loss. So is this general idea relatively clear? Any questions? Yes. this featureized model question. So it depends whether it's included in the vocabulary. So you might put in the training set. The way you might have it in the training set is if you limit the vocabulary based on a frequency threshold, basically. Yeah.
The features are always, one word behind or two words behind, or should it be using a...
So one thing about featureized models is they give you the ability to design any features that you want. So this could also include like a bag of word feature for all of the previous things in the context. There's other ways you could design the feature set as well. Any other questions? Okay, cool. So that's a basic idea. Now, if we look at this model, what problems are handled by this? And essentially, this model still doesn't have the ability to share strength between similar words. And the reason why it doesn't is because we're still learning an individual feature for each combination of words we've seen in the context and words that we're predicting. And because of this, we wouldn't be able to, update these, we wouldn't update the probability of giving and delivering simultaneously. There's no interaction between the features here. So that doesn't make it possible to easily capture these kind of things. However, it does capture this. It does fix this problem here because we have a feature regarding what was the second previous word. And the second previous word could be doctor, and that might allow us to predict that the next word was Smith. So this problem is solved here. The model doesn't handle long distance dependencies, but it could be made to handle long distance dependencies if we design the feature space like we just talked about before. If we added more bag of words features for the entire context, et cetera, et cetera. Okay. Any questions about this? Yes.
Would skipping more words than just one word help it model long distance dependencies?
Would skipping more words help it with long distance dependencies? So yeah, that's actually a good question. If we looked up one previous word, two previous words, three previous words, four previous words, we could make a very, very big vector, right? We could make it up to 50 previous words or something like that. But if you think about it, the connection between the 49th previous word being giving and the current word being something is pretty tenuous, right? So at some point, it would probably be, if we were going to design this model, in practice, we have better models using neural networks than this. But if we wanted to design this model to make it better at capturing those dependencies, I would probably, have different parameters for up to the previous 3 words or something like that. And then all the other words would share parameters, for example. All the other previous words. I have a question. Why is it okay to compare subword models with character-based models, but not the other way around? Why is the comparison relationship not symmetric? So subword-based models and character-based models, that's a good question. Let me see. So basically, if a subword-based model is able to generate any sentence in the language, then it's okay to compare a subword-based model and a character-based model because they both have the ability to generate the same sentences. So in technical terminology, they both have the same support. They can generate the same set of sentences. One thing you should be a little bit careful about is you need to make sure that the denominator here is the same between the models. So like if you have a subword-based model and a character-based model, you should make sure that you're not dividing by the number of characters for one model and the number of subwords for another model. I mean, it seems elementary, but it's a mistake that you could make. So as long as the denominator here is the same and the models are able to generate, like all the sentences in the language, it would be possible. Comparing word-based models with character-based models, if the word-based model is not able to generate like Wilmerding, basically, if it doesn't have a model that would allow it to generate Wilmerding, and instead you are having it generate the UNC symbol, then that would not be fair for the same reason I mentioned before. It's a lot harder to generate Wilmerding than UNC. Yeah. Yeah, so this is like a bag of words classifier in one way. So a bag of words classifier, if you remember from the previous class, what we did was we looked up each word in the sentence, and we calculated the probability, how much that affected the probability of a particular tag going up or down. And what we're doing here is something very similar. We're looking up the previous word, and we're calculating how much the probability of a particular next word going up or down is. The big difference between this particular model that I introduced here and the bag of words classifier is it's also using the position information. So it's also considering not just given whether the word A exists in the context, but it's also considering directly whether the previous word was A or whether the second previous word was given. So in that way, that's a little bit different than the bag of words model. Okay, so let's say, let's move beyond linear models. So linear models, the biggest problem with them is they cannot easily learn feature combinations. And what do I mean by feature combinations? This is a good example here. We have students take tests, teachers take tests, students write tests, and teachers write tests. And maybe, maybe all of these are probable sentences, but if you look at the comparative probability between them, the first one would be higher, the second one would be lower, third one would be lower, fourth one would be higher. So one thing you should note here is that if you look at the individual words and the position of the words, none of them on their own are indicative of whether the probability should be high or low. So basically, students being 2 positions ago is not enough to determine whether it's high or low. Take being 1 position ago is not enough to determine whether it's high or low, et cetera, et cetera. So the only way you actually know whether the probability will be high or low is taking the combination of 2 different pieces of information or more. So what can we do about this? How can we create a model that allows us to extract these features? So one way we could do this, and this is kind of what the Ngram model does as well, is remember combinations as features. So we could have individual scores for things like students take and teachers write, et cetera, et cetera. The problem with this is now we would have features over every single vocabulary item for every single pair of vocabulary items. So that becomes on the order of vocabulary to the 3rd features. That's a lot of features to save. Now, let's say we want to expand our context even further. Now it becomes v to the 4, v to the 5. Ngram models also, remember a lot of things, but they only remember kind of positive counts. So that helps them maintain the size to be a little bit smaller. Another way we can handle these feature combinations is using neural networks, which I'm going to get into next. So neural networks, I think most people, yeah. So they can't be expressed, maybe that's a little bit of an overstatement. They can't be expressed easily by something that does a linear combination of features such as the ones that I talked about here. So it couldn't be expressed easily by just features about whether a particular word occurred like one time away, and other features that based on whether a particular word occurred two steps away. So neural networks, I think most people are familiar with these by now, but just to give a little bit of a recap, neural networks, the original motivation for them was based on neurons in the brain, where you have synapses, and electricity goes into the synapses, and when they reach a threshold, they output an electrical signal. But in reality now, the things that we call neural networks are basically computation graphs, and computation graphs are a graph that expresses a computation, but it's a computation that is constituted by a bunch of smaller, less complicated computations. So to give an example, if we have an expression x, we have a graph x, where x corresponds to a node. This might be an input. And a node could be a tensor, a matrix, a vector, a scalar. So a scalar, is a single value. A vector is one dimension worth of values. Matrix, 2 dimensions. A tensor is any arbitrary number of dimensions. Then we can also have nodes that correspond to the result of mathematical operations on other nodes. So in this particular case, we have a node describing the transpose. And because the input is a vector x, we have the transpose vector. So now our expression looks like this. An edge in the graph represents a function argument and also a dependency. And they are basically pointers to nodes. So the edge is pointing to this node here. A node with an incoming edge is a function of the edge's tail node. So this transpose is a function of x. And importantly, a node knows how to compute its value, and the value of the derivative with respect to each argument times the derivative of an arbitrary input. So basically, the reason why this second part is really important is because it allows us to calculate the gradients of, for example, inputs or parameters at the beginning of the graph. So I'm going to talk about that in a second. Functions can be nullary. So in other words, inputs that take no other value. They can be unary, like the transpose here, or binary, like a matrix multiply. Computation graphs are generally directed in a cyclic because you need this condition to make it possible to calculate them using the algorithms I'm going to talk about in a second. And interestingly, graphs can be expressed in different ways. So this graph here and this graph both express the same computation. They just do it in different ways. So we have an input x and an output a. And if we have a special node, which is like x transpose times a times x, then we could also express the same computation here with a smaller and more compact graph if we want. And so let's say we have a graph like this. This expresses a function, and we can name name nodes in the graphs. So basically, if we do y equals this, that's basically just naming this node in the graph. And then we have a whole bunch of other unnamed nodes in the graph as well. Okay, so this is a computation graph. And what we can do with it is we can run some algorithms over it. So we have graph construction and forward propagation. So forward propagation in topological order computes the value of the nodes given the inputs. For some people, if you're familiar with neural networks, you might not think of these as two different things. You might think of them as the same process, especially if you use something like PyTorch. Basically, there's two different ways of doing this. One way is to create the graph first and then calculate the values afterwards. Another way is to create the graph and calculate the values simultaneously. If you do it simultaneously, it's called eager execution, which you might have heard of before. So forward propagation looks like this. So basically, we have a defined computation that we would like to run. And all of the inputs we already have calculated, so that's fine. Then we have all of these nodes that could be calculated because all of their inputs already exist. And then we just step through in any arbitrary topological order until we get the outputs. So the second set of algorithms that we can apply are back propagation, which processes the examples in reverse topological order, calculating the derivatives, and parameter update, which moves parameters in the directions of this derivative. So back propagation, basically we start at the end. Notably, the end, the last node in the graph, doesn't have any following nodes. So what we do is we define this as a function we'd like to minimize or maximize, and we set its gradient to 1. We assume it's a scalar also, so we set its gradient to 1, and then using the derivatives that we know how to calculate for each of our nodes, we now do reverse topological order and calculate these gradients. I'm going to go into more detail in next class. In the assignment that we're going to do involves actually implementing some of these things, so I think you should have a much more concrete idea of how things work. But that's a basic idea. And the nice thing about neural networks is now we aren't restricted to, a particular type of function. We're restricted to a much larger class of functions that can be that can be created using all of these more elementary functions that we have defined in, a neural network toolkit or something like this. So yeah, just to give an example, this function itself is not implemented in, many neural network toolkits, but every neural network toolkit will have things like transpose and matrix multiply, so we're able to create this more complicated function using the simpler parts. Okay. Any questions about this? Yes.
So on slide 26,
Which one was it? Sorry. Let me.
20.
Yeah, sorry. I forgot to add slide numbers again. I apologize. What's the title? Or
Where the edge and node and everything.
okay.
Yeah.
Mm-hmm.
So now I understand why the transpose is here on the right-hand side.
Oh, sorry. This is an example specifically for the transpose function.
Oh, okay.
Yeah. Sorry. That wasn't very clear. So that's over here. Was there another question here? Yeah.
How much do you recommend you work on the assignment for next class?
How much do I recommend you work on the assignment before next class? As much as you think you need to do to get it in on time by the 20th. But I think you don't need to do it before next class. You can wait until next class and start working on it then. Although I can't estimate how busy you will be, for example. But, yeah.
Next class is going to be a lot more.
Yeah. So I would only recommend working on the assignment before next class if you're already pretty familiar with like neural network toolkits. I definitely would not do it before next class if you are not 100% comfortable already. Okay. So yeah, so that's the basics of neural networks. Now going back to language modeling, how does this apply here? So there's a lot of different ways to do language models. The important thing, I'm sorry, I actually forgot to add a slide about this, but the important thing is if we go back to the example that I had before, We had this very specific way of calculating scores from a language model, which specifically consisted of, lookup 2, lookup 1, and a bias. And so this is a log linear featurized model, but we can use any variety of function to calculate these scores. And if you remember from 2 classes ago, we kind of had the idea of feature extraction and then calculating these scores. So what we can do is we can think of a neural network as a way to extract features that are then used to calculate the scores over the next vocabulary items. So going back here, I'm going to talk about one specific example. I meant to have the general slide before the specific example, but I'm going to talk about one specific example of a neural network that can be used to calculate these features and scores. So what this is it's a feed-forward neural network language model. And the basic idea is we look up vectors that represent the previous n words. We run it through some feature transformation. In this case, it's a hyperbolic tangent over a weight matrix multiplied by this vector representing the words plus a bias. And that calculates some features here. And based on these features, we multiply by another weight matrix over the calculating scores of the vocabulary. We add a bias and we get some scores, which we can then feed through the softmax and get some probabilities. So instead of looking up the scores over each vocabulary item directly based on the previous words, we look up some vectors, some embedding vectors, if you will, and run them through a nonlinear transform, through a linear transform in a nonlinearity, calculate some features from this, and then calculate the scores based on this. So this can allow us to do a couple things. This can solve 2 problems that I talked about before. The first thing that it can solve is that it allows us to extract combination features. Sorry, I relocated my slides from another presentation, and I realized I'm missing a few that I thought I got. So the thing, it solves 2 problems. The first problem it solves is that it allows us to extract combination features. And the way it can do something like this is it basically, this embedding and this embedding, when they're run through this weight matrix here, can interact in various ways. So just to give an example, let's say the first element of the first vector and the third element of the second vector were active. And the first element of the first vector was indicating that the part of speech of was an article or a determiner or something like this. And in the second vector, the third element being positive is, corresponds to the fact that 2 words ago was a present tense verb or something. So if we say the lookup, like and the and this and all of the determiners have this feature active, and then all present tense progressive verbs have the third feature active, then the when you run it through the nonlinearity and the linear feature transform, you could do something, you could have something that looked a little bit like this. So this might be a little bit hard to see from the back, but basically, you could calculate a feature in the purple vector here that would be positive in all cases, or that would be highly positive in all cases where the 2 words ago was a present progressive verb and 1 word ago was an article, for example. So yeah, I'm really sorry that I missed adding this slide demonstrating feature combinations, but basically this gives you the ability to extract features that are, number one, abstracted. So they allow you to do things like consider all articles or all present tense progressive verbs. And they also allow you to do combinations, which is like, this is true and this is true. So I'll fix my slides next time to try to give a concrete example of this if this isn't very clear. But basically, what this allows you to do is this allows you to have similar input words, get similar vectors. So as I mentioned before, like for example, if it's an article, you could get a similar vector for all articles. Also for words that are similar on the output side, you could give them similar vectors. So we talked a little bit before about how bicycle and car might appear in similar contexts. So if things appear in similar contexts, the words in the softmax matrix here might have similar values as well. And also similar contexts will get similar hidden states. So for example, if giving and purchased will have similar words following them, then, or bought and purchased will have similar words following them. After this feature extraction function happens, we would expect that these purple vectors here would get similar values. So yeah, I apologize. This is a bit abstract without examples, but this most importantly solves the problem that we cannot share strength among similar words. It also solves the problem of not being able to use combination features and say, like, if the previous word is this and 2 previous words is that, we would like to upweight this. So are there any questions about this? Yeah.
So can we think of this as a neural network with one hidden layer then? So instead of going from input words directly to probabilities, we have kind of a hidden layer in the middle that is kind of some sort of encoding for those input words.
Yes, exactly. So this is a neural network with one hidden layer. So this would be the hidden layer here, and this would be the output of the hidden layer. Yeah. I have a few questions on Zoom very quickly. Oh yeah, so there was one question. What is this here? This is concatenation. So basically what we're doing is we're taking 2 vectors and we're concatenating them together into a single vector. Yes, question.
So the only thing that is not solved yet is was the third point, which is long distance.
Right.
Right. So will it be fair to say that if we have a deeper network, long distance will be solved?
Yeah, so that's a very good question. If we had a deeper network, would long distance be solved? So the answer is, if we have exactly this, so it depends on what you mean by deep, I guess. But if we have exactly this, like model structure, then we would not have it making the network deeper. So in other words, adding more hidden layers to process the words in a more complex way would not solve the long distance dependency problem. And the reason why is because we're still only inputting 2 words, right? So we need to give more input. Interestingly, maybe one of the first papers on neural networks for natural language processing was in 1989. And the basic idea, 1989 or 1988 or something like that, but the basic idea, what they did was they just had a model that looked exactly like this, but they concatenated 10 words together and used those 10 words to do text classification, to do translation, to do other things like this. And so it is, you know, this model, theoretically, if you had an infinite amount of data and a very wide or deep network, should be able to solve all of NLP. And the reason being is neural networks, there's a famous thing that neural networks that have sufficient capacity, that are wide enough or deep enough, even if you only have one layer and it's wide enough, can solve any problem, can, you know, model any function with a few light assumptions. So that would include taking in a whole bunch of concatenated vectors representing a sentence and, you know, predicting the next word. However, despite the fact that theoretically it would be able to do that, that's not a good model architecture to model language. So there's lots of other options that I actually mentioned here, which is we're going to be talking about recurrent neural networks and self-attention transformer networks, which are much better ways of capturing that information. Let me check. Okay, so I see the Zoom questions were resolved. Are there any other questions from people here?
Go back to the first lecture.
Yeah.
You said that feature extraction is almost converting the information. How would you look at that in terms of neural networks? Whether or not is that you extracting features rather than giving it out?
Yeah, so that's a really good question. So going back to the first lecture where I talked about how feature extraction is losing information. Another way to look at this neural network here, actually, sorry, before I go into this, I'd like to point out two things. One, there's actually a code example of implementing a neural network in PyTorch linked from the website. So I'm not gonna talk about it in class today, but you can take a look at it if you want. It's implementing basically exactly this model. The second thing is that you can also do something called tying, like embedding tying. And basically what it does is you note that the embeddings on the input side and the embeddings on the output side are both over the entire vocabulary. So you can basically share the parameters between the input side and the output side if you want. So let me go back to the main question that I had here, which is feature extraction is basically losing information. It's removing information that you don't want to be, that isn't relevant for making predictions. And to give just one example, let's say the difference between bought and purchased is basically, it has virtually no effect on the next word that you're going to predict, which is pretty reasonable, right? They're pretty close synonyms. And if that's the case, what you can do is you can make these embeddings the same for bought and purchased. And if you make these embeddings the same for bought and purchased, then you'll have exactly the same predictions regardless of which one you use. That is probably a better choice. Like that's extreme, right? You know, it's completely removing the difference between them, but that's a better choice than treating them completely independently and trying to learn them completely independently. So it's removing the information about the identity, but by doing that, it's sharing information between the training examples for the two. So that's the basic idea here. Another thing so maybe that's the best example. Any other things? Okay, so why is the W matrix here called the softmax matrix? Maybe a better thing to call it would be the matrix of the linear transform that happens directly before you apply the softmax. That would be more accurate. It's more like I'm abbreviating that much longer, more wordy thing into the softmax matrix. So The softmax function has no parameters. It's just a function that renormalizes things into probabilities. So it's correct that it doesn't have a matrix on its own. Any other questions? Yeah.
Is there a reason why we have the vector of A before the vector of giving by concatenate?
Is there a reason why we concatenate, or in that particular order?
Even though R is after given, you have concatenated R before giving in the vector.
So that's a very good question. The answer is it doesn't matter which order you concatenate them in. You could concatenate them in the order 1, 5, 3, 4, 2, or something like that if you had 5 vectors. The reason why is because the matrix multiply is permutation invariant. So no matter what order you put the input in, if you also make the order of the rows in the matrix multiply here permuted in the same order, it wouldn't make any difference in the function you calculate. So basically, if you permuted them in the opposite order, you would basically expect this W1 matrix to just be learned in the opposite order. Yeah. Anything else? Okay. If not, that's all I have for today. Thanks a lot, everyone. Sorry I missed the important slide on feature extraction. I'll add that next time so we can catch up.